Okay, hello again. Now I will talk about much more complex methods than just correlations. I will have this talk in two parts. First part, it will be introducing you what are these deep neuronal networks, about some nomenclature, what they are doing and how they are structured. And in the second part, I will show you some code as before to show you how you can use those neuronal networks very easily with MATLAB to analyze your own data. What was really amazing about this deep neuronal network is that this was typically extremely difficult task for computers to make good image classification. So, for example, discriminating that this is dog, it's not something that, it's easy to define. So, if I would ask you what are the features of dog, you wouldn't say that this is something what is up in the sky. Or saying that this picture is in category hat is also not that obvious. So because it's so difficult to define object, because they can change orientation, size, colors, and so on, computers were very, very poor on this task. But with this deep neuronal network, it turns out that it is possible to do very, very good discrimination. And here are some other examples that usually what this network do is that they have multiple categories and they are rating in which categories this object is the most likely. So here you see part of the cheetah, and this network correctly guesses. The second best guess it was that it is leopard. Here you have picture much more complex, and again it guessed correctly that this is a bullet train. Here it's magnifying glass, so here it guesses it as a scissors, and to be fair, it's a little bit resembles scissors, and this hand glass it was as a second choice, so it wasn't so bad, but it's not yet perfect. But nevertheless, to guess that in this picture is this bullet train is something what 15 years ago no computer scientist would say that it is possible to do it with high accuracy. So because of those advances in image processing by neuronal networks, now they are applied, for example, for self-driving cars. So, this what was something, story of the dreams, that you sit and car will drive by itself. Now it's reality. And there is reality because those neuronal network can really nicely discriminate if it is other car, if it is pedestrian, if it is a sign, what number is on this sign. And because they can discriminate those things, now it is much easier to design algorithm so these cars can navigate and keep the lane and so on. Interestingly, exactly the same algorithm which I use for image recognition can be also used, for example, for solving problems like playing Go. So Go is a very difficult game. It has many more options than chess. And here the strategy is that you have to put stones, so you will surround opponent stones and you are winning those stones. And nobody believed that in the next 10 years we can write some programs which can solve it, because there is so many different possibilities. And what this neuronal network did is that, some patterns can also repeat regardless if it is here on the middle of the board or somewhere on the side. Similar patterns should be played probably in some similar way. And because this network is so good at analyzing images, it started learning what are the good type of positions to achieve and what to do in this position, in given position, and how to recognize positions regardless where they are on the board. That it turns out to be also great for beating world champions in Go. So Also, most of you have iPhones, and for voice recognition, it is also run on artificial neuronal networks. So here is an example of some spectrogram. So this is sound in this frequency domain. And, you can think about it also as pictures, that, those things can be analyzed like pictures. Here it is also important to look at the history that, one syllabus depends on the previous and so on to interpret speech. But again, neuronal networks perform now much better than any other algorithm at speech recognition. So one thing to keep in mind, that data is data, and those things which are great for image recognition can also be used for help us with neuroscience projects. That here, for example, if you can discriminate different type of cheetahs, maybe you can also have scans of control subject and patients, and even if by eye you don't see any differences, maybe this deep neural network can find some features which are kind of maybe distributed between different brain regions to help to discriminate patients from control subjects, and I will show some more data about it later in talk. That networks can also analyze videos, well, it is also can be used very much in neuroscience. So, for example, one thing what we are doing in our lab is that we took neuronal network which was trained to recognize different poses on videos of people, and now we are applying it to look at the rats. So here, what the task is that rat has to, in this stop, reach for a food pellet. And by looking exactly how rat is reaching for this food pellet, how it's opening its paw, we can see if the rat, how rat is affected by stroke. So normal rat will reach almost like a human. The stroke rat will rather just put this paw and drag this food pellet. So by looking at this nuances of the movement, it's really possible to see how well rat, for example, is recovering from stroke, from motor stroke. But the problem is that to analyze those hours of videos, it takes a lot of time of a student, and so it takes a lot of time, and it would be good to have some automated methods. So for that, we are developing some network which now can do quite well at discriminating which rat are affected by stroke, which rats were control rats, and so on, and to what degree the stroke affected their movement. And what is interesting is that, the same network with a little retraining can also perform well on other tasks. Like, for example, here's another motor task where rat has to walk on the two parallel beams, and student now is sitting for hours and is measuring how many times rat slip from this parallel beam to somehow quantify a degree of movement impairment. And again, with these neuronal networks, we can do it a quite good job. So here we can do so far as good job as a poorly motivated student. Here we can do as good job as a well-motivated student. So accuracy is almost perfect. So what is also nice about those methods is that they can be easily applied from this type of video analysis used for car driving to behavioral data with very little changes in network architecture. And similar algorithms which are designed for sound processing can be used, for example, to analyze LFP, EEG data, and also spike trains. And again, on the end of this talk, I will show you some code how to do it. Okay, so first reminder that, if you see cat, in fact, what here is picture, what computers see is just a set of numbers. But it's not only what computers see, this, each number is reflecting what is the intensity of a given color. But it is exactly the same case with us, that when signal, when light is coming and modulate our photoreceptors, then each receptor is like, this little number activated or not to some degree, and later from those signals from each receptor, we have to create some image. So on our photoreceptors, there is this set of numbers, and later somehow our brain is creating this image that we can recognize, oh, this is cat. And now I will describe how neuronal networks are taking this set of images and creating, recognizing cat. Okay, so this is generic picture of some neuronal network. Usually it has some input layer, so it means that here is the value of 1 pixel in image, second pixel, third pixel in the image. This information is now passed to this artificial neurons, and I will describe soon what I mean by that. And this information is now sum up and transferred to output neurons, and depending if it is this neuron activated or this, it means that this is image of class 1 or image of class 2. So like it will discriminate if it is picture of cat or a horse, for example. So what is the single artificial neuron? So typically it is just very simple that here you have this input signal, so you have this here in this case 7 input signal, and each input signal is multiplied by some weight. So you can imagine like signal is coming to synapses, and if synapse is stronger, the signal will have bigger influence on neuron. If the synapse is weak, it will have a smaller influence. So exactly it is done here, and this influence is multiplied by those weights and sum up. So it is the simple linear model what we are talking about. Now, what happens is that later there is this nonlinear function, in this case sigmoid. So what it means is that, like in real neurons, if there is too little activation, nothing will happen. If there is, large activations or large activations plus something, it will result in exactly the same spike. So if signal is only a little bit higher than threshold or much larger than threshold, it will result in exactly the same spike. And it's similar here, that those activation function is that it means that this is amount of input and this is amount of output. So in typical neuron, in biological neuron, when there is a signal below threshold, then nothing happened on the output. Output is 0. If signal passes threshold, then the output is 1. For some computational efficiency, what happens in these artificial neurons, they are, instead of using the step function, they are using sigmoid, which is just smoothed version of that. And recently, they discovered that it is even better to design those artificial neurons when instead of sigmoid is this type of function. So nothing happened when signal is smaller than threshold, and when it is larger than threshold, then it just linear increase. So how it connects to this? Well, so each of those circles is exactly this one of neurons. So this neuron takes value of those pixels, multiplied by some specific weights, and now if the signal passes this threshold, then it is passed to the output neuron. And this output neuron, again, is summing up this activity, and based on this is giving answer. So the question is, how to train this network, how to change those synaptic connections that this network can do something useful. So this is the main difficulty. It's not to design this network, but how to train those networks, how to adjust those synaptic weights so network can do something good. So here I will give you a few slides which I borrow from some online PowerPoint slide which I found, showing giving some intuition how this training is done. So again, here you can think about this input layer as values of pixels in image. Here you have some neurons which have some weights, and this is output neuron. So usually what you have to train those network, you have some signal. So let's say the value of pixels for the first image is 1.4 and so on, and it will be class 1. This will be these three values will be class 0, and this will be class 1. So you have these two different classes, and on the beginning, those weights are completely random. So we are starting with some random weights. Now we are giving first example, those first three numbers. We are multiplying by those random numbers, and we are getting something on the output. And now, what we can do is, well, the first class, it should be 0. So this neuron is giving us not so good answer because it's giving us 0.8, and it should be 0. So there is quite a large error around 0.8. So what to do about it? Well, now what happens is that if we know that what is the error, now we can modify those weights in the following way. So if we know that this neuron is giving too much value, we can look which of those connections was giving the largest input. So let's say that this was the strongest connection, it was the biggest contribution to this 0.8. Well, in such case, we know we can mostly decrease value of this synapse. So we will decrease value of this synapse because this connections was giving us the most contributions to the error. And we can do this also in the propagate this scheme to the previous layers. That we know that this neuron contributed the biggest error to this. So now we will see which neurons, which connections were contributing the most to activity of this neuron. And again, the connections which were the most contributing to the error, they will be mostly changed, and so on. So what you will adapt this is that now you will present some another example, and look what was the error, and if the error is small, you will make only very small modification, and you will repeat it for every single image. So basically you are giving this tens or hundreds of, or sometimes thousands or millions of different examples, and with each example we are looking what was the error network, and next you are modifying those connections to make this error a little bit smaller. So the crucial thing is that you are making those very small modifications at each step. And after this thousands of times repetitions, you will get network which is performing exactly what you want. So I describe you this kind of simple neuronal network, and it's called as a shallow network because it has only one layer. Now, all these miracles in image classification is done with those deep networks that what they have this multiple layers. And before it was difficult to train because this backpropagation of errors, it was not so easy because, to find how much this neuron contributed to the final error, this error signal was quite washed out. And now there are some a clever trick with normalizations and with these different activation functions, which makes it more easier. And also what is important that now we have much bigger data sets. So now we can train those networks for longer time, give them more examples, and get better predictions. So one other thing is that why those deep networks with this many layers would be better than such shallow networks. And the interesting thing is that those shallow networks, in theory, they can learn perfectly any classifications problem. So if you give two images, you can train this shallow network to discriminate those two images perfectly. The problem is with generalization, that these deep networks are much better at generalizing that, some small changes in image will not change in which categories those images are classified. So in this network, it was, small rotations of phase could cause some unpredictable changes in the output. Here, it is much more better to learn some, invariances in pictures, and we will talk why it is like that. So, in our visual system, it's very similar that we have this many layers of processing. That, for example, in V1, first we have those cells which are detecting specific orientation. Later you have cells which are detecting some combinations of edges. And later in IT cortex you have this complex cells which are combining these complex edges and responding to some specific images or faces, regardless of orientation or size and color. So by doing this hierarchy, it seems to be really helping with this invariance recognition of objects. And one of the reasons for this invariance to detecting correctly objects is what is called complex cells. So complex cells, which here are in simplicity represented, they are doing the following, that they are looking, for example, this complex cell is looking at neurons which have the same type of receptive fields which are tuned to detecting this let's say 45-degree lines, but they are looking it not in one place, but they are taking information not from one such place field, but also from multiple place fields in some bigger area. So this cell will be activated regardless if the edge was detected here or a little bit shifted to left or a little bit shifted to right. All those, if any of those cells was activated, this complex cell will be now activated and pass this information to the upper layer. And the same structure of the simple cell and complex cells is repeated over and over, and it gives these abilities to detect some good features and later to make those features invariant of a specific position or size. So this was mostly designed by hand in this network by Poggio, and it performed quite well, but it was his, by design, said that, those neurons will be detecting particular edges and so on. But with these deep neuronal networks, by applying these training procedures, networks can learn by itself to detect such things. So here it is those different layers of some neuronal network, which was trained on recognizing different natural images. And what you can see is that if you look at receptive fields of neurons here, they are mostly tuned to some lines, some changes in colors. In these middle layers, they are now the receptive fields are mostly activated by much more complex shapes, and each of those little images is showing receptive field of one neuron. So this is neuron 1, 2, and so on, and similarly here, each of those squares is showing what particular neuron in this middle layers was responding to. And in these top layers, the shapes are even more complex, and here it looks like some bird. Here you have some neuron tuned to detecting parts of the car. So it seems like there was a lot of cars in this data set. So a lot of those receptive fields are detecting some round objects, probably. But again, what is really amazing here is that it seems to be mimicking how our systems, our neuronal system, is processing informations, that it learns to detect this on the beginning, very simple features, later combine it, and on the end detecting quite complex images. So what are the tricks that these deep neuronal networks can do it? So one of the advantages is what is called a convolutional network. So here what we said is that we could have neurons which are detecting particular orientation. And on the beginning, when people were training networks, then each of those neurons, so this neuron is looking at this patch of the image, this neuron is looking at this patch of the image, and so on. So each of those neurons had to independently learn what are the good features to detect in this patch. And there was also other neurons, detecting, which were responding only to this patch. So some neurons were in this patch detecting horizontal lines, others learned to detect vertical lines, and so on. But each of those neurons which receptive fields had were in these different patches had do it independently. So people thought, well, maybe what is good for looking at this patch, maybe those features are also good for this patch. Now what they mean by this convolutional neural network is that they are teaching all those neurons simultaneously that they have the same type of receptive fields regardless where they are looking at. So now it reduces number of these weights which has to be trained, because when training, let's say, for these patches and what the features are to analyze this patch will be also good for analyzing this patch. So something learned for this, it will be applied also here. So this is what is called this convolution, because as I told you about the spike trains convolution, that the same kind of kernel, it will be now moved around this image. So it means that whenever in this image is this vertical line, this neuron will be active. And similarly, there is another set of neurons tuned to this horizontal, which will learn to be tuned to this square lines with, let's say, 45 degrees, and so on. The other thing is pooling. So pooling is this invariance to the orientation, to the exact location in space. So this is what complex cells were doing. So in this artificial neuronal networks, where they use what is called pooling layers, actually they have neuron which is looking to multiple neurons with the same, which are tuned to the same feature, and what it does, it just looks which of those features, which of those neurons had the highest value. So basically, this neuron will be telling, was anywhere there some horizontal line. So in this case, you see that this neuron is receiving this image of the stick, which is exactly good orientation, so it will be highly activated. Here is kind of part of the stick, so it will be only a little bit activated. So this neuron will only say, okay, in this patch of image, there was some stick, but I don't care exactly at which location. So this convolution layer, which reduces number of weights which needs to be trained, and this pooling layer, which helps to decrease resolution of the image to just focus, is there some specific contours regardless of if it is a little bit to right of the left, greatly help to in performance of this artificial neuronal networks. And here's another example of such what I was saying, that if here you have, let's say, how much a neuron was activated by, let's say, horizontal line. So this neuron doesn't see any horizontal line. It has very little activation. This neuron see quite a bit of horizontal line, so it has 6. So you have here this 4x4, 16 neurons. So after this pooling, you will have this image will be reduced only to those 4 values. This will be saying, okay, in this part of the image there was some edge, here it was even bigger, and so on. And in actual networks, we are repeating this convolution nonlinear stage. It means this sigmoid or this rectify linear function with nonlinearity, and later after this pooling, looking, taking only maximum values from those receptive fields. So this is just to give you general idea what are the main structure of such networks. The other thing when talking about neuronal networks, sometimes people talk about recurrent networks. And when we think as a neuroscientist about recurrent networks, we think about, typical cortical circuits, which is highly interconnected, that when signal is coming to layer 4, for example, then it goes to upper layers, then from upper layers go to deeper layers, and all of this is highly interconnected, and signal is going in those loops. It's very difficult to train such networks, artificial networks with such recurrent connections. So usually when people say recurrent network, it is network which is using specific type of neurons called long short-term plasticity memory neurons, LSTM. So those neurons are like normal neurons, but in addition they have this one recurrent connection, so they can remember what was their previous state. So this neuron, to get activated, take into account what is the input and also what was its previous state. So basically, this what usually is referred as a recurrent network in this deep learning community. It is not actual what we would imagine as a recurrent network, but rather network where neurons have this self-connections. So this is just to clarify that it's really yet not discovered how to train some really highly complex network with a lot of feedback connections, and so far there is no good algorithm to train such network with recurrent connections. So this is so far the best what we can do. And why it is good for? Well, if you have, for example, videos, it's really good to know not only what is in particular frame, but also what was in frame before and before then frame. So by keeping this track what was the previous states, it helps to analyze these sequences in images. The other interesting development in artificial neuronal network is what is called autoencoder. And it is something similar to what Mark was describing and talking about principal component analysis. Here, it does something similar, that it finds some interesting projections how to compress data to the most informative dimensions. So basically, what this network does is that it takes image. Here, it, let's say, is 200 neurons where this image is coming from. The second layer is less neurons, and here is some bottleneck with only 30 neurons. So you see this number of neurons was almost reduced by 10. And here it's exactly the same network as before, but in reverse. And now you don't want to classify images. You don't care what class the image is. You just want this network to reconstruct exactly the same image what was given on the input. So it seems like a very dumb task that, asking network to give on the output exactly what was given on the input. But the trick here is that this bottleneck. So to reconstruct this image, signal has to go through these 30 neurons. So those 30 neurons really need to have some good features to reconstruct this, to allow to reconstruct this image. It is like, finding this best 30 principal components to reconstruct images. But what it does, so principal components is this linear methods. Those components are orthogonal to each other. Here, this is highly nonlinear manipulations. So those components can be find some things which principal component wouldn't be able to find. So here is example that there are some sample data set, for example, data set with handwritten digits, and network has to somehow learn to discriminate these digits. So here they train this autoencoder to learn those numbers and to decode those numbers to represent. And they use this 10 or 30 neurons in the middle. So when you take those images and do just principal component and plot it on the first two principal components, you will find this kind of scrambled image. And each color represents different numbers. So it seems like number one is those numbers ones are quite well separated from the rest, but other numbers like 0 and 9 seems to be quite close to each other and difficult to discriminate. So PCA can do some reasonable dimension reductions, but if you apply this autoencoder, it can find much better projections. And again, this is done in unsupervised way, that here we are just asking network to learn to reproduce the same image as it was presented. So we are not saying that this is class 1, class 2, class 4. It learns by itself that certain images have something similar, so it learns this very useful representation, and later when you plot in this 2 dimensions, based on this bottleneck activity of neurons, then you can find much better discriminations of different digits. So I thought that this is very, very cool idea that, you don't need to label data, you just give, some spontaneous activity data, and the system would learn what are the main features of this activity just by trying to compress it. And in my lab, we work a little bit that we designed some autoencoder with this convolutional layers to help us to make those digits to be more so that small shifts in positions of the numbers will not affect performance. So adding this convolutional layer and pooling layers, it allows us to make this much better even discrimination. So again, we didn't say to this network, learn to discriminate digit 1 from digits 2. Rather, try to represent properly digit 1, 2, and so all the digits, and it learned to do it by itself, some good representations that later, so it did much better job at separating those different images than any principal components analysis would do. And similar autoencoders here were applied, for example, for some analysis of videos on the internet, and this network made quite a bit news because by giving hours and hours of YouTube videos, some neurons here learned to recognize human faces, but also there were neurons which learned to recognize cats' faces. So it seems like cats are as popular on YouTube as human. Okay, so how it can be used in neuroscience. So here is an example of one of the papers where they use it in neuroscience. So they just took scans of MRI scans of people, control subjects, and subject with Huntington's disease. And just by applying the same autoencoder principle, they just reduce data. And here they plot this data after reductions. And here each dot is one patient. So as you see, this network in this completely unsupervised way, like PCA, found this nice 2 clusters. One is for controls, and the other is for patients with different degree of severity of symptoms. So patients which were ranked by physicians as having high symptoms were mostly on the one end of these clusters, other people with low severity on the other end of this cluster. It seems like this network didn't do perfectly, that there are some people with this dot, it means that it was patients with high symptoms, but is classified in this control subject. But nevertheless, it's amazing that by giving this data, computer learn by itself this deep neural network to make very useful representation of this data. And so why neuronal networks are so good? Well, what you learned so far is mostly about these linear methods. Neuronal networks are almost linear. So you have this first linear stage where each input is multiplied by some weight and added up. But the miracle comes in this nonlinear stage, that after the summing up, later is this nonlinear stage of decision. It is 0 or 1. So this, by having such set of neurons, it allows to make classification in a very to segregate clusters in the way which wouldn't be possible with any single line. And we can talk about it later about details. So one thing also about this, why deep neural networks are so good, is that before, when it was more difficult to have this large amounts of data, the simpler models, like linear models, they need less data to be trained to perform well. So before, when we were somewhere here, those linear methods were quite good. And because this neuronal networks has this thousands or millions of neurons, and each has this tens or hundreds of weights, it is enormous amount of parameters which needs to be estimated. So it was very difficult to do it with limited number of data. But as amount of data increases, it is as much as, those standard methods can perform. They quickly achieve some asymptotes. But with this neuronal networks, because they are so flexible, because they have so many parameters, giving more data, it helps to improve their performance. And now that we have this fast computers, a lot of data, and we learned some tricks how to train this really, really large neuronal network, we are somewhere in this regime that these deep neuronal networks are beating up any other older algorithms. Okay, so now how you can make use of those networks and amaze your supervisor. Well, so if you look at MATLAB website, there's really well done tutorial and documentation how to make such networks. And there's just one-click examples that you can click and run those networks and classify different images. So on the MathWork and MATLAB website, you have already good examples of data sets and some networks, deep convolutional networks, how to classify those images. So if you play for 1 day with this, you will see that it's really not scary, that with little background you can design your own networks. So I will not talk much about it. But what I found a little bit more challenging is to do some simpler things, like, for example, how to use this deep neuronal network to analyze signals like EEG or local field potential. So there I couldn't find some ready-to-use examples. So for that, here I will show you some code which you can use to try to discriminate, for example, between different type of EEG signals. So let's say you have EEG signal from control subjects and from a subject with some disorders, or subjects which are involved in different tasks, and you want to automatically discriminate based on EEG what type of the signal it is. And in this case, I was using it, for example, to detect when the seizure will happen. So I had signals from rats which had some seizures, and I was looking what are the differences between signal during some periods without seizures versus signal which is right before seizure to help to predict when seizure will occur. So what I prepare for you guys is some artificial signal, and here what I will be discriminating is between two sinusoids. One sinusoid has 90 Hertz, other has 21 Hertz. And you know, with simple Fourier analysis, you can quickly and easily detect it. So what I did, and here is some code of how to generate such two sinusoids. So it is just 4 lines of code to generate such two signals. Now what I did is that I added random noise. So this picture on the bottom is the same as this, but with added noise. So the amplitude of this noise is larger than the amplitude of those sine signals. So this is what you will get. So the sine here is hidden inside of this noise. So you see that the y-axis here has much larger amplitude. Here it was between -1 and 1. Here, because it's added noise, it has this amplitude between -3 and 3. So this is the line which is adding to the sinusoid with just normal Gaussian noise. So now, by looking at some short fragment of such data with Fourier transform, it would be much more difficult to discriminate those two sinusoids. That if you would have, you know, a long fragment of data, you can do it. With short fragment of data, it would be much more challenging to find this small difference in frequency. So I will apply neuronal network to take around 100 samples of such signal and tell me if it was 21 or 19 Hertz sinusoid. So this is a longer fragment of this data. So here is 1,000 samples, and again, red and blue are those sinusoids with different frequencies with added noise. And what I did to train this data, I took this 100 samples, and I took those samples at some random points. So here I said I want, for my training, segments of 100. I will have 1,000 of such segments, and I will take those randoms, those beginning of those segments will start at some random places. And here what I'm doing is just creating in that one array is just those putting together signals from red trace, and in this that2 I will be putting these segments from blue trace. When working with MATLAB, it's also very important to prelocate memory for some variables. So what I mean, here in each loop, I'm taking one of those fragments and adding to this array. So I can do it, you know, increase the size of this array at each iterations of this loop. But what MATLAB actually do when we are increasing size of the array is not just adding to the end of this array, is looking where in the memory I have enough space to fit this already existing array plus one more line. So it is actually taking this, copying in new place this a little bit increased array. So it takes a lot of time if you would do it without prelocation of memory. So because we know already what will be the size of those arrays, then I'm already saying, okay, reserve this amount of memory, and now in particular places in this memory, I can insert those segments. So this is, especially for large arrays, it can save a lot of time. Okay, so here is next part of the code. So now I just put together those segments from from red signal and from blue signal. I create some group variables, so it will tell that signals here are from group 1, this is from group 2 for the training. And now what I will take is, as you heard in previous talks about cross-validation, I cannot take everything to train my network because I can overfit. What I will do is that I will take 80% of these samples and use it for training, and I will choose randomly 20% of those samples and use later for the testing. So this is what I'm doing here, creating this random samples of 80%, and everything what is left, the last 20%, it will be used for testing. And here on the end, I'm putting this data in some 4-dimensional array, which is used the format for this neuronal network as an input. So I have to reformat this data a little bit. Okay, so what network we will use? So we have this input data, but this is 100 samples for each segment. We have this 1,000 segments. Now we will have this layer of neurons. It will be this 50 filters. So I will look for some features which are good for representing, for discriminating those different classes of signals. Here it is this nonlinearity. So if signal is in this neuron smaller than some threshold, it will be 0. If it is bigger than some threshold, it will be exactly what was the value of the input. And on the end is pooling size. It doesn't matter if some feature it was detected on the beginning of the segment or on the end of the segment. This neuron will be activated whenever this feature is present. And on the end, I will have those 2 neurons, and whichever neuron is more active, it will mean that this is class 1 or class 2. And this simple schematic, this network can be described by this few lines of MATLAB code. So here I'm just defining what is the size of input image. This duration here, variable, it is just 100, saying what is the length. I'm saying that I want this convolutional layer with receptive field size of 70, and it will be 50 different filters. Next is this rectify linear layer with this nonlinearity. Max pooling is here. And on the end, I'm defining with those three lines that there are those 2 neurons. So this neuronal network can be easily defined like that. And what I commented here is that, as I said, it's very easy to make network bigger, to add those pieces and like stack Lego blocks on each other and make it bigger. So similarly, I can add few other lines, so it will be another convolutional layer, another nonlinearity, and another max pooling to make this network bigger and better for processing more complex signals. So when I run this network, here I have to define few more parameters, like for example, this define how many times I will present the same data set. So it's sometimes not enough to present once the data set, because those modifications to weights are so small that it's good to present many times the same data set. And here I'm saying I will be presenting 10 times the same data set. And also the other important parameters is learning rate. So I'm saying that the changes of those weights cannot be bigger than this 1% of original weight. So very, very small adjustments. Here is the line which is actually training this network. So it is just one line. I'm giving here all the data. Here I'm saying what is the group. And here I'm saying what are the layers, what we defined before. And here the options. So this line of the code, it is what is training all this network. And if I run it, and later, so this line will train all the weights. So later, when I run it, it will also produce this picture. So this picture will tell me that when the first time this data set was presented, the error was around 50%. So it was exactly at the chance level. But very quickly, this network started reaching this 100% performance on this training data set. So later here, what I'm doing is using this neuronal network for classification. So here I'm giving this 20% of test data set, so the data which were not used for training this network, they were put aside for testing, and here I'm using it to test how the network will perform, and accuracy was also 100%. So to summarize the signal which was given here, it was really difficult to distinguish with any other methods. And with this simple neuronal network, it is easy in a matter of seconds to train this network to find that one signal has some slightly different temporal features than other signal. And some just optional fine-tuning is that here I was specifying what is the learning rate. This is still quite a bit of adjustment, so we may want to continue learning for some task to have this adjustment even smaller. So now with this, we can make this much more fine-tuning by saying, oh, don't modify synapses too much because they are close to optimum. Just make some very small modification to make it, perform few percent better. So this is something what you can add on the end of the code to retrain this network, to continue training this network with these smaller errors. Okay, so discriminating to sinusoids, not a big deal. So I created some other signal. So here you have this red and blue. So what are those two signals? So here are two ramps through two triangles, which are overlapping. So here, both signals have exactly the same frequency. The difference is following, that red signal will have some bump added on the beginning of this ramp, and the blue signal will have the same ramp, just added a little bit later. So those two signals have exactly the same frequency. The only thing that is difference, you can think as some phase locking, that there is some phase locking, that in certain condition some other signal is locking to the beginning of this ramp, and in other cases some signal is locking to the later part of this ramp. And again, this would be too easy for networks, so I added similarly this random noise. So now the noise is much bigger than the amplitude of the signal. So again, this is what you will get. And it is, if you replace those few lines of the code which were used for generating sinusoid with those few lines of the code which are now generating those ramp, and you will use, so only replacing this part, and you will run exactly the same code, so exactly the same network, and if you run it, you will get almost perfect classification. So again, for me, it was quite amazing because I couldn't think about any other method that, can so quickly and without some human engineering find some differences between those two signals. The drawback to this is that it's good for finding some differences, but to ask this network what was the differences which were important for those signals, it's a little bit more complicated, and I will not have time to go now into that. So as what I showed here, you can easily do these things in few lines of code in MATLAB. If you want to do some more complex things, like, for example, trying to discriminate videos of rats doing different tasks, if it is stroke or control rat, then you will need some more complex tools. And, for example, there's published by Google some libraries called TensorFlow, which allows to create much more complex network. But for that, you also would need to learn Python. That those things are not using MATLAB, they are using Python. So if you want to do something really more complicated, you would have to probably go beyond MATLAB. But as I said, for local field potential analysis, or for example, if you want to classify images from your histology, MATLAB should be more than enough to help you to apply these neuronal networks. Okay, so that's all what I have about this. Any questions? So that's a good point. What I mentioned here is the following, that because to have, sure, we can connect neurons in the similar way as in biology, so have a lot of this feedback connection and so on, and it will be very difficult to train this network to make any useful classification. So it will be very difficult to make some complex video classifications with this network. So people are adding this little self connections, which helps neurons to remember what was their past. And what is important is that now you are not looking only at one frame of image, but you are also keeping in memory what was the previous image, and so your response will be affected what was the past activity. So for something like speech processing or video analysis, this poor version of recurrent networks, it is what is usually used in deep learning. Does that answer your question?
This is self-connection, right?
Yeah. So this is what I'm saying. It is a poor version of what you would consider this actual recurrent network, but because we do not know how to train those big recurrent networks, so it is the best what we can do so far. So here, those networks and just feed-forward networks are trained with backpropagation. And when you have this highly recurrent networks, it's much more difficult to assign those errors, and the backpropagation algorithm seems to fail. So those networks are trained in exactly the same way as standard networks without this self-recurrent connections. Does it answer your questions, or your questions was different? Well, so everything depends on your data set. In this case, to discriminate those two sinusoids, I use something like 1,000 examples, but probably it would also do well if I would reduce it to 100. So I think everything depends on complexity of the problem. To discriminate those images of dogs and cats, before it was one of the difficulties was that people didn't have enough of such label data. So one of the Stanford researchers got her career off because she created painfully such enormous data set where by hand she labeled this is dog, this is cat, and so on, which allows to train those networks. So more complex things will require more training. And again, here, because this is quite new field, we really don't know what are the rules, how much data you need, what type of architecture you need. It's a lot of, trial and error.
Let's actually revisit it. Think like keep an elephant somewhere in the brain, right? Do you think that actually we can publish something now in the methods like easily, saying that actually these patterns were found in such a network? I'm trying to think of an example. Like let's say a gamma person. I'm not going to talk about anything. And you say, well, I've trained my network with like a lot of data, but then like all the detection I do is based on this black box matching, and I don't give you any return output to detect it.
Yeah, so that's
a reviewer yourself, but
Well, so if you apply this and it performs well for discriminating, for predicting when the seizure will happen, who cares? It's interesting to know what are the features, but if it works, that's the most important, that it can help people, to know when the seizure will happen. So, but in other cases, if you're writing some basic science paper, then definitely it would be significant drawback that you cannot easily know what this black box is relying on. Now, there is quite a bit of work trying to find out what this black box is doing. So when I was, for example, showing this receptive fields here, it is that they apply different methods to try to figure out what features those neurons are responding. So it's not something easy, and those are just approximations, but it is possible to get some idea. That in this case, for example, one of the methods is, for example, to give some white noise and change this noise to maximize activity of this particular neuron, then you can get some ideas. So it's not easy to get information, but if you try hard, you can get it to some good clues. Exactly. So it is like, you try to come to this particular place. So first, you will take a very fast flying airplane to more or less come to correct distance to somewhere, to Vancouver area. And from Vancouver area, you will take, decrease your speed, your learning rates, and now you will take bus to get closer. And when you are close to this building, then you will walk, so you can go to particular. So if you would be traveling at this airplane speed, you will not be able to correctly come to this building. So this is like on the beginning, those learning rates are big to allow the network be in more or less correct place. And later with fine tuning, it is like walking exactly to particular building. Okay, so I will be after this workshop for some time, and we can talk more. Thank you, guys.